Good morning. Um, Here we are back with more thermodynamics, moving on to our last chapter in thermodynamics, and that's chapter 20. Um, and it's calling itself the second law of thermodynamics, and that has to do with a concept called entropy. So entropy is an important concept. We want to get a feel for this. So let's take a look and see what we have here. So in this chapter, second law of thermodynamics, entropy, we're going to be looking at heat engines, we're going to be looking at refrigerators, air conditioners, heat pumps. They actually say we're going to come back and look at entropy here at the end. Instead, we're going to start with a couple of examples to start getting a feel for what entropy is and what the second law of thermodynamics is telling us. And when we do that, then we'll start looking at these devices and how they operate. So that's our plan here. And then there's probably a few more, here we go, some more entropy-related concepts. So again, those first items, that's just a list. Just for your organizational benefit if you want to use that. So the second law of thermodynamics is a statement about which processes occur and which don't. Let's see, here's one. Here's one statement of the second law. The second law of thermodynamics tells us that heat does not, it flows spontaneously from a hot object to a cold, but it doesn't flow the other direction. And so if I just leave objects out there, and we've talked about this before, so I hope we've kind of given you guys a sense of what's going on here. If we start with two samples of material, one's at a higher temperature than the other, say it's two containers of water, and they're put into thermal contact with each other, through conduction, the faster moving water molecules bump into the slower water molecules, and that motion gets transferred. And that motion we refer to as energy. So kinetic energy is just kind of a name keeping track of what kinds of molecular motion is taking place. And so what it's saying is, it's just kind of a statistical statement. It's saying that if you have a sample of water with faster molecules and slower ones, and you mix them together, then you're going to get kind of a statistical, not random, but a statistical mix throughout the entire sample. You're not going to start with something at a lower temperature. You're not going to have slower moving molecules move into faster molecules and the slower ones transfer their energy over. If we look at what happens in molecular collisions, it tends to bring the molecules closer to an average rather than continually push them farther apart. We'll see. So in any case, it's the statistically most likely distribution of molecular energies. That's the one that we see. So entropy, let's just write this down. So we're going to do a couple problems in straight entropy. It turns out that the entropy, which is a measure of the disorganization or the randomness of a collection of molecules, entropy depends on how much heat we transfer into the object, and it depends on the temperature at which that heat is transferred. Now, it seems a little funny. I mean, I can see the idea that if I transfer energy in, I'm going to get a more disorganized or a more random distribution of molecular kinetic energies, because there's just more energy available to the molecules to do more sorts of things. So in this example, what it's saying is I have one sample of water. This is just one. And it started out at 20 Celsius, and now I switched it so the water is now at 50 Celsius. Now when it was 20 Celsius, there was kind of an average velocity, an average energy of the water molecules. And at 50 Celsius, there's also a distribution of energies for those molecules. But we know that at 50 Celsius, on average, the molecules have more kinetic energy than they did before. But still, it's this statistically most likely distribution of energies that we end up with. Now, to calculate how much the entropy went up. So in going from 20 Celsius to 50 Celsius, at 50 Celsius, the water molecules have more energy. They're going to have speeds that they weren't moving at before. It's going to become a wider range of molecular kinetic energies. That's what we consider to be more entropy. And it turns out that for molecular systems like this, it seems, I don't know, a little funny, that you can actually calculate that. You can get a numerical value that tells you kind of the disorganization or the randomness of the molecules. And you can do that by integrating the heat over the temperature. So let's try that. What we'll say is that for the water, now we're just looking at the water, we're not looking at the container. For the water, as we transfer in little bits of heat, so let's start transferring heat into the water, dq, 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 dq. Every time we transfer a little bit of heat in, the temperature goes up. Well, in order to calculate how much the entropy is increasing, the delta S, S stands for entropy, we need to know the temperature at which each little piece of heat came in. So what we do is we take this expression for dq and replace it with mc dt, and now what I have is I have an integration in terms of the temperature. So now what I can do is I can follow that increasing temperature, and this integral will make sure that each little piece of heat that comes in, the appropriate temperature is used in the denominator. That's going to give me the correct answer. Now, what that leads us to in terms of a formula, if I'm taking a sample of some material, adding heat, how much does the entropy go up? It goes up mc natural log of T over T naught. That's a quantified amount of entropy increase in the sample. So let's try this. What we'll do is we'll say this is a 100-gram sample. It's 100 grams after it goes up in temperature. We started at 20 Celsius. We're going to 50 now. I got to use Kelvin. This is one of those temperature formulas with the T sitting there. It's not a delta. It is not a delta T formula. And so I've got to use kelvins on this. And so the starting temperature, once converted, is 293 kelvins. Final temperature, 323. I plug the numbers in, and the entropy increase, I find, is 40.8 joules per Kelvin, which means nothing to me, right? Because this is the first entropy calculation I've ever done. Is what you're thinking, I'm guessing. Anyway, this is one of those things you get used to it, right? I guess you try and build some familiarity by doing a bunch of these examples. Now, why did the number come out to be what it is? Well, it's related to sample size. If it was twice as large of a sample that underwent this, that would be twice as much of an entropy change. So it does depend on sample size. It also, other than that, it really comes down to the temperature range that we're working with. It's kind of the ratio of ranges. And then it has to do also with the specific heat of the material. Now the units, joules per Kelvin, those are the units. Okay, those are units of entropy. And so those are going to be standard units. Now, what the second law of thermodynamics says is that for any closed system, the overall entropy goes up. So entropy is always increasing. Let's look at another example and see an example of this. Now this is just one sample of water being heated. Now I'm going to move on to two samples of water, sample A and sample B. This one I'm going to start out at 20 Celsius and this one at 80. Each one is 250 grams. Since they're the same size sample, I'm going to put them into thermal contact. Now that could mean I either mix the water together or I just put their containers in thermal contact. The final temperature is going to be 50. If I go through and do a calculation from chapter 19 using specific heats, I'm going to find that the temperature is going to meet right in the middle because the sample sizes are the same and the specific heat is almost a constant. So we know what the final temperatures are going to be for the sample. So let's go in and ask what happened to the entropy of each of those samples. Let's see what we've got. And so the entropy on sample A is going to be given MCL and final temperature over initial. Now this one started at 293 Kelvin and it went up to 323. That means the entropy went up. Okay? So when I heat something, entropy is going to go up. And it went up by 102 joules per Kelvin, 102 entropy units. Meanwhile, what's happening with sample 2? Well, sample 2 is being cooled down. So sample 2 actually is going to have a decreasing entropy. If these are, these two samples here, these represent the same amount of entropy here as here, because they're both at the same temperature, and they're both in the same material, same phase, same mass. So this is going to be a decrease in entropy here. I follow the same formula. The natural logarithm automatically, if I'm lowering the temperature, the natural log of some ratio less than 1 will give me a minus sign. So the minus sign takes care of itself. And that's minus 93. So when I add these two together, now what we can do is we can treat these two samples combined as a closed system. It's a closed system because all of the energy transfers that took place were between these two samples. Okay, and so if we think of it, it is a closed system. And so what we're saying is, if I look at the total entropy that happened here, the delta SA, delta SB, that ended up increasing the overall entropy, 9.07 joules per Kelvin. So that's kind of interesting. What looks like kind of a symmetric problem. The 80 Celsius water came down to 50, the 20 Celsius water came up to 50. Why didn't it just cancel out so that there was no change in entropy? Now, what's happening is, it's the temperature, if we go back to the starting formula. Notice that if I'm transferring the heat at lower temperature, that's more of an entropy change than the same amount of heat being transferred at a higher temperature. And so what that formula tells us then is, when I mix materials together that are at different temperatures and allow them to reach an equilibrium temperature, overall the entropy goes up. So the second law says in all reactions, in all things that happen in nature, overall the entropy at best is staying even, but essentially in all cases in nature the entropy is gradually going up. Now think about this. Apparently the universe can never go back again. Anytime you mix hot and cold water together, people are very cavalier. Oh, some hot water, cold water, I'll mix them together. Ooh, once you've mixed the hot water and cold water together, the universe can't go back. That's a process that the second law of thermodynamics says statistically just isn't going to happen. Think about this. If we had done this process and reached this final state, is there a way that this just goes back to like it was, and you go, not as a closed system, not unless I bring in a heating element in a refrigerator or something. These materials by themselves now, this process can happen one direction, it's statistically driven, and once that has happened, that's it. If you had a container full of pennies or something, and one half of the container was all heads and the other half of the container was all tails, and then you started shaking it and randomly moving them around, the heads and the tails, how long until it's just a random mixture of heads and tails? And then if you say, if I just keep kind of switching this thing back and forth, is there a way the heads and tails would separate themselves out again? And statistically you would say, yeah, there actually is a chance that you could just take a bunch of coins or a bunch of red objects and blue objects and put them down in a box, all the reds on one side, all the blue on the other, and you just kind of randomly shake it around, and you look, and you randomly shake it around, and you look. And the more you just let things randomly happen, the more it becomes mixed. And it's pretty unlikely, now it's not impossible, you might look down one time and go, oh my gosh, look, the reds and the blues all sorted themselves out. So this second line is statistically driven. You can actually calculate the likelihood that these two containers would spontaneously go, and it's like, it's not going to happen, right? So anyway, this is the calculation of entropy, and entropy is going up, and anytime we see the entropy like this go up, it's an indication that it's not a reversible process. It will not reverse, at least not on its own. Okay, now that we've got kind of this entropy thing in mind, let's take a look at heat engines. So now I think we're better set up. We can take a look at heat engines and kind of analyze these. Now if you're thinking in terms of heat engines, you know, this is like the internal combustion engine in a car, a nuclear power plant, anything where we're generating a high temperature region through a chemical reaction or a nuclear reaction of some sort. So we have this kind of an analyzed a diagram to analyze these. But let's say we have a combustion chamber, and inside the combustion chamber we generate this really high temperature material. So like in a car engine, if it's an internal combustion engine, you ignite the gasoline, you run a chemical reaction with gasoline and oxygen from the air, and you generate some different products, some CO2 and water, but you generate a high temperature. A lot of potential energy is released and converted into kinetic energy. And so here's this high temperature region. Now, what you can do is you can follow the flow of that high temperature region, the flow of energy away from it out into the environment. Now if I just ignited some gasoline out in the environment, you would heat everything up and the energy would spread out, and the environment everywhere would be a little warmer than it used to be. But in a heat engine, what we do is we divert some of that energy that we've generated. So using a mechanical system, you know, instead of just letting the heat escape, what we do is we run it through a mechanical system where we actually make things move. You know, a car engine. We start it up, and the car engine's turning, and we engage that with the drivetrain and the wheels, and we drive our cars around. So in analyzing the heat engine, we have a high temperature region, typically a combustion chamber, and then we have a low temperature region where the energy ends up, and that's typically out in the environment. Now, we're going to divert some of this energy to the engine, and so we can say we would like to divert as much of the energy that we've generated, or much of this heat, we would like to convert into work. If possible, for every 100 joules of heat we generate, it'd be great to get 100 joules of work coming out. Turns out that most heat engines are no more than 20 or 30% efficient. And there's different reasons for that. But there's some reasons why heat engines are never 100% efficient. There's always a limit, and we'll see what that limit is. So again, we're trying to get out as much mechanical energy as we can. Let's see how that might work. All right, so here's that very same diagram. I turned it sideways. So here's a combustion chamber. Here is a high temperature region, and then here is the low temperature region. Here is the heat leaving the high temperature region, running through the engine or the motor, and then we're trying to get as much work as we can. Whatever energy is left is going to go directly into the environment. So let's come up with some numbers here. First of all, I want to come in and define an efficiency. How efficient is my heat engine? I'm going to define efficiency as the work divided by the energy, the thermal energy that we've generated in the high temperature region. So again, if I generate 1,000 joules of energy here, how many of those can actually be converted into mechanical energy, something that will operate my car, generate some electricity, something like that. So I just put some numbers in. I said, let's imagine that for every 1,000 joules of thermal energy that we generate in the high temperature region, we were able to get out 350 joules as work, something that we can operate a vehicle or generate some electricity. Well, to me, that sounds like an efficiency of 350 divided by 1,000 would be 0.35. That's about 35%. Now, energy conservation tells us this. So, if we generated 1,000 joules and we were able to get 350 joules of useful work out of that, it suggests that the remaining 650 joules just goes out into the environment. So when I'm operating a heat engine, I would like as much to go into work and limit the amount that goes right into the environment. We're going to find out that 35% is actually a pretty good number. So there's a couple ways I can write my efficiency. I can write it as work divided by energy input. Now, I can also say that the work is QH minus QL, and that gives me this formula. So this is the one with work directly in here. We're going to find out this formula is useful too because it's written in terms of ratios of heat. The QL and the QH, the energy going into the environment, the energy being generated. Now, where the second law of thermodynamics comes in is looking at this efficiency term right here. And let's see how that happens. If we've got a combustion chamber and we generated heat, QH, and at a temperature of TH, then the entropy decrease. We generate a bunch of heat, but then we remove it from the combustion chamber. It's a steady, ongoing process, but the heat continues to be removed from our combustion chamber. Well, that's a steady decrease in entropy, specifically related to the heat leaving the combustion chamber. That's going to have a minus sign on it. And that was our formula for entropy. If we've got a certain amount of heat leaving at this temperature, that'll tell us how much. Now, on the environment side, we're going to have some amount of QL and leaving, and that's divided through by the temperature on that side. That'll tell us the entropy increase of the environment. Now, what the second law of thermodynamics tells us is for a closed system, once we've included the engine and its environment, that these two numbers combined have to be at least 0. And in most cases, they're going to be larger than 0. So the entropy is going to go up, or at least stay steady. Under the most ideal conditions you could imagine, the entropy decrease here would match the entropy increase here. Now, since these heats that are transferred at different temperatures, what that does is we can write this in terms of this ratio, flipping the symbols around. The energy going, the low temperature, or the low temperature heat flow into the environment divided by the high temperature heat flow generated in the combustion chamber needs to be at least as large as the ratio of temperatures. So it's saying the best we could ever do under ideal circumstances is QL over QH equals TL over TH. So that's ideal. Let's see what that would do to our formulas. So this was our efficiency, and that was written in terms of the Q's. What's the theoretical best efficiency that we could hope for our heat engine? And that's going to depend on our operating temperatures. So let's say we've got a heat engine, the heat's being discharged into the environment. That's at 300 Kelvin. And our combustion chamber is at 500 Kelvin. That's not a super high temperature combustion chamber, but those are the numbers I happen to put in. So 300 Kelvin, 500. The best we could ever hope to do would be a formula where we've taken out the ratio of the Q's and replaced it with a ratio of the temperatures. Remember that the QL over QH is always going to be larger than TL over TH. Now, we would like to keep this as low as possible, but it's always got to be larger than this. So by using this ideal formula now, that's going to put an upper limit on our efficiency. And by plugging the temperatures in, it turns out that for these operating temperatures, the best we could do, given the way that nature works, given the drive towards statistically more random states, is 40%. It says that for these particular operating temperatures, our efficiency is going to be really, really low. Now, there's a way around this, you could imagine. What we could do is to get a more efficient engine, to boost the efficiency past this 40% limit, we could operate at higher temperatures. So if we can get our combustion chambers operating at the highest temperatures, practical, in terms of material properties, we could boost that efficiency. So, you could go up to, 600 Kelvin, 700, I don't know. At some of these temperatures, most materials are going to start to show a lot of fatigue and wear. And so maybe for an internal combustion engine, we're not going to do better than, for the ideal efficiency, 40 or 50%. Maybe we don't do much better. And if that's the case, then we're not going to do much better here. Now, for power plants, again, for a power plant, you want to operate at these really high temperatures that you possibly can. So maybe you could boost this. There's not much of a good method for lowering that low temperature number, right? We're kind of stuck with the environment of the temperature. I mean, we could move everything to Alaska or something, and then the temperature outside would be lower, and that would boost our efficiency a bit, but that's not very practical. So we're kind of stuck with the environmental temperature as the temperature into which all of this heat's going to go. Now, another thing to keep track of here is, here I am, I'm operating this power plant or something, and I'm getting 35% of the work, or 35% of the heat energy is being converted into work. What eventually happens to that work? Well, we generate a bunch of electricity, we use that to operate some appliances, maybe we use it to operate a heater of some sort, but all of that energy eventually will become heat. Okay, so energy doesn't stay organized. You can think of work as kind of being the organized form of energy. The energy becomes disorganized, the entropy increases even more, and that energy just spreads uniformly through the environment. So all of this energy that we generate eventually just leads to that heat being spread through the entire environment. Okay, so now it also says heat engines and refrigerators. We're going to look at refrigerators a little later. Refrigerators operate by reversing this process. They actually use work, so you plug in a refrigerator and you transfer energy from the low temperature region into the high temperature region. Okay. Now for the heat engines, it says we're only going to be looking at heat engines that run in a repeating cycle. So let's... the lower part's important here. The way we've defined QH and QL and W, we're treating them all as positive numbers. So keep that in mind. It's just the amount of energy. We're not going to use minus signs on these for these examples that we look at. All right, so what are some possible heat engines? Well, here's a steam engine. So this is kind of handy because we can show this pretty easily. So here we have the heat input. We boil a bunch of water, we get a bunch of steam, and the steam's at really high pressure. So we generate really high pressure water vapor, and that high pressure can be used to push a piston. So here is an intake valve and it's open. When that opens up, this fills with this high pressure steam, and then that pushes the piston. Now, we don't want the piston to stay pushed in that direction forever, so we close this, open up an exhaust valve, and let the steam come out. The steam's cooled down, so you drive the steam in at high temperature, use it at the high pressure, and then you release that. And then steam can go back into a condenser and it can be pumped and recycled. So the QH that we're generating here is being converted into work at that location where you're driving that piston. Right? That's PdV work at that location. Now here's another example. This is what they called a reciprocating type. So a reciprocating type is where you go through a cycle. This thing kind of cycles back and forth. And so there's a cycle, and then you repeat the cycle many, many, many times. You let the steam in, drive the piston, release the steam. You let some more steam in at high pressure, drive the system, and then it cools down and you release that steam. This, on the other hand, this is a continuous example. Here, if we just have high pressure from the steam, and we have this turbine set up, you can just keep driving the high pressure steam at the turbine blades, and then this is where the intake occurs, and then here is where it exhausts. And then you don't have to go back and forth with these pistons in these different reciprocating styles. You can just have a continuous turbine that's being spun by the high pressure steam coming in, and as you can see, the pressure is reduced once it's pushed against those turbine blades. Okay, back to the internal combustion engine. So here is what's operating still a majority of car engines, and so we're going to have an intake valve where a fuel-air mixture, gasoline and air with oxygen in it, enters a combustion chamber. Okay, so we're drawing it in. Here's the fuel inside, and now this closes. And then this is compressed, and when it's compressed at the top, there's an ignition that takes place. And that ignition drives the piston back very forcefully. So the idea here is this. If I'm going to get work out of this, it has to be relatively easy to compress the gas. So the opposing pressure is not so large, but then when we ignite it, the pressure just goes really, really high. So the idea is to drive the piston back many, many times more forcefully than what it takes to initially bring the piston into position. And then we can release that, open up the exhaust valve, push out the exhaust materials, and then draw in a new mixture of air and fuel. All right, the efficiency, we're just repeating some of the things that we saw on those earlier slides. And so the efficiency we're going to define as the work divided by QH. W, the work, because of energy conservation, is equal to QH minus QL. And so we've replaced that, and then we got this different form. Again, I try and go through and get rid of these periods. I don't always feel like equations. They're just confusing with periods. Anyway, cross that one out too. 1 minus QL over QH. So let's try an example. Here's a car. They tell us right out that this car has an efficiency of 20% and that it produces 23,000 joules of mechanical work every second during operation. So here's this automobile engine. And it sounds to me like if it's 23,000 joules per second, that's 23,000 watts or 23 kilowatts, which is our power unit. Now you guys know that car engines are rated in kilowatts, right? Like you wouldn't rate them in horsepower? Really? Horsepower? That's kind of a funny name for a unit. Anyway, so we've got 23 kilowatts of power. Now this is saying how much heat input is required and at what rate is energy being discharged. So let's take a look and see. We're just trying to keep track of all the energy here. So here it is. Here's my car engine, here is the combustion chamber in the diagram, so that's part of the engine too, generating the heat. And then we're going to divert some of that. A lot of it's just going to go out into the environment. So 23,000 watts of power. Okay, I wrote down horsepower. So it's 31 horsepower. And that's a good amount of energy. 23,000 watts is enough to take a car and move it at constant speed at a pretty good clip. The car engines just have to be bigger. Those extra horsepower are typically so you can climb hills and so you can accelerate. But if you're just going at constant speed, that works pretty darn well. So 23,000 watts, and it's only 20% efficient. So I set my efficiency equal to 20, and then I took my efficiency equation and flipped it around to solve for the QH, and it turns out this car is generating in the engine, in the combustion chamber, it's 115,000 watts. So that's 100% of the energy that's being generated. It's much more powerful than what this work rating is. And that's because 80% of the energy is going right into the environment. So every second, 115,000 joules of energy are being generated. 92,000 joules are going right out into the environment. 23,000 are being diverted and used to propel the car, to offset air resistance and things like that. All right, so heat engines, this is saying, wait, no, heat engine can have an efficiency of 100%. This is another statement from the second law of thermodynamics, and that's what we've already seen. So we started out with some of those statements up front to make sure that we were clear about that. So, right. So it's another diagram here. So we're saying that heat's coming out from the combustion chamber, and this diagram would claim that 100% is going into work, but that can't happen. And we're using the second law of thermodynamics. We're using our understanding of entropy to make that determination. So what this is really saying, some portion of the heat always goes directly into the environment, and that the efficiencies, the ideal efficiencies, are going to depend on operating temperatures. So if we can change the operating temperatures, we may be able to work to a more efficient setup. All right, now let's talk a little bit about what's called the Carnot engine. So we looked at some of these engines in those diagrams before, but now what we're going to do is we're going to take an engine and we're going to analyze it on a PV diagram. So all that stuff we did in chapter 19 with the constant pressure, constant volume, constant temperature, adiabatic processes, we're now going to take combinations of those different processes we looked at and analyze some engines. Now there's one particular type of engine, it's referred to as a Carnot engine, that in some ways is really useful to analyze. And here's why. This is kind of a theoretical idea. Ooh, let me see what it says here. It says the Carnot engine was created to examine the efficiency of a heat engine. And in some sense, this Carnot engine is kind of a theoretical idea. So engineers try and develop engines that follow some of the things we're talking about here. Let's see what we've got. And so I'm starting off with a PV diagram. The Carnot engine operates between two different isotherms. So I'm going to have a high temperature and a low temperature. Now that looks like the formulas that we've already developed for heat engines. We've talked about efficiencies based on operating temperatures. So what happens with a Carnot, this theoretical engine? The Carnot cycle consists of an isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Now I know, going back to chapter 19, the adiabats and the isotherms were a little harder. The adiabats were the hardest. processes to work with, but that's what's present in a Carnot cycle. Now, if we think about this, we're going to start at this high temperature, at a fairly low volume and high pressure, and we're going to let an expansion take place. So there is this expansion that takes place, and it's adiabatic, it's isothermal, and during that isothermal expansion, heat is coming in. So that's where the heat comes into the engine. So heat is coming in, and that heat is leading to a lot of work is being done. If you see, this expansion is happening at a pretty high set of pressures. All that area under the curve, that's all work. And so that's our biggest portion of work right there. Now, once we get to point B, and we've had all of this heat come in, then we thermally insulate the engine from B to C, and we say now we're going to continue to expand, but this time it's going to be an adiabat. Now remember, in an adiabat, Q is equal to 0. So Q is equal to 0 in an adiabat, and so that process right there, no more heat is going into that process. So this was step 1, this is step 2 here that we're talking about. Now we're getting a little bit more work here and here. So now once we've expanded fully, so what, if this is a piston being driven, once we've expanded that fully, then we're going to try and reset the engine. We're going to try and bring that piston back to where it was. And we're going to do that, first of all, following an isothermal process from C to D, and then another adiabatic process from D to A. And so that's what the whole process looks like. Now, what makes a Carnot cycle, 2 adiabats and 2 isotherms, what makes this handy to analyze is that the heat is all coming in at one temperature. And that's kind of what we imagined when we were looking at efficiencies of engines, that all the heat was coming in at a high temperature, was leaving the combustion chamber at a high temperature, and then all the heat was leaving the engine. I guess that is how it worked. The heat was coming into the engine at a high temperature. The heat was leaving the engine at a low temperature. And so that makes it easier to analyze. Okay, here's a Carnot problem. And so, or some Carnot formulas. So let's see how this works. From A to B, there was an isotherm happening at the high temperature. Now, for an isotherm, delta E, the internal energy of our sample inside that engine, is going to be 0. And so QH is equal to the work along that process, and we've derived a formula for that. So the work along an isotherm is nRTH ln VB over VA. That's the work we get through that power stroke of the engine. Now, as it continues to expand adiabatically, now the Q is stopped, and so the additional work that we get is going to be 3/2 nR delta T. So that's actually the temperature here is dropping. This is going to give us an additional amount of work. This is going to give us a positive amount of work that's coming out through that process. So we're going to get work out in the first step, and we're going to get an additional amount of work out in the step right here. So again, in BC here, the temperature is dropping. Delta T is negative. That's going to cancel the negative sign here. Now let's look at the next isotherm. Now we're going to start compressing. Now we're back to delta E is 0. QL is equal to the work done during this process. This is going to be nRTL ln of VC over VD. So this is how much work is required to push the piston back into place so that we can start the whole process over again. And then here's the last portion of that compression. Q is equal to 0, and the work done here, the work that we have to put in, 3/2 nR delta T. Now, the delta T here is the opposite of the delta T here. So the work that we got along the adiabat during the expansion offsets the work we have to perform during the adiabat on the compression. These two works cancel out each cycle. So what we're left with then is that QH is equal to this amount, QL is equal to this amount, and the work that we get out of this engine each cycle is this minus this. So if I'm going to go in and calculate how much work, I can take this number, subtract off that number, that will tell us how much work we've done. Now, for the adiabats, so these parts cancel, and then we're left with the QHs and the QLs. Now, if I get back to the efficiency formulas, the efficiency formula is 1 minus QL over QH. And, well, there's my expression for QL, and here's my expression for QH. So QL over QH is this ratio of quantities, and the N's and the R's cancel, and I'm left with TL over TH. So TL over TH is the ratio of the operating temperatures, and then I have these logarithms of these volume ratios. Using the adiabat formula that we introduced back in chapter 19, we can show that the ratios here is 1. That logarithm on top and the logarithm below, it's the same quantity. It's going to be the same. And so this part cancels out. And it says, for a Carnot cycle operating under these conditions, the ratio of Q's matches the ratios of temperatures. And that is, that's what the second law said, is that under ideal conditions, the ratio of the Q's will match the ratios of temperatures. So our prediction here is for a Carnot engine. A Carnot engine would be operating at the ideal conditions. It would be operating at an efficiency of 1 minus TL over TH. And that's why you'll see a lot of reference to this in the textbook. You'll see it in the examples that they use. They like to come back to a Carnot engine as an example of an engine that's operating at ideal efficiencies. Okay. And that's, they've written down the ideal efficiency here. We had done that earlier. So for us, we'd already looked at the entropy. We had already looked at how entropy limits the efficiency. So I hope that was useful to have those early slides so we kind of saw where this was all coming from. Okay, so it's saying that real engines typically come only within 60 or 80% of this highest imaginable efficiency. So, if the ideal efficiency is 50%, maybe a real engine only gets 35 or 40%, kind of like that example that we looked at earlier. All right, so let's look at a few more examples with these heat engines. Now, this example is referred to as a phony claim. So an engine manufacturer makes the following claim. Somebody invents a new engine, a new heat engine, and says that the input per second is 9,000 joules at 435 kelvins, and the heat output is 4,000 joules at 285. So we want to check and see if this seems reasonable. So here is the example set up. And again, we've got that familiar diagram. So we're going to generate some high temperature, generate a high temperature environment and have that heat flowing into our engine. Here is the heat leaving, here is the work, and the numbers they've given us, the number that this person came up with, is the heat going in is 9,000 joules, the heat coming out is 4,000 joules. Well, that suggests, it didn't specifically say this, but it suggests that the work we're getting out is 5,000 joules. Now that's a pretty good efficiency. You know, if we're getting 5,000 joules out and we're putting 9,000 joules of, we're generating 9,000 joules of heat in the combustion chamber, that's looking like an efficiency 0.556 or 55.6%. Is it really possible this person's come up with a heat engine operating at these temperatures which is so efficient? Well, let's check. So if we plug the operating temperatures, the person who designed this engine also provided us with information about the operating temperatures. And if we plug these into the formula, so the person suggested that the energy going out into the environment is at 285 kelvins. The energy being generated by the engine is at 435 kelvins. And that gives us about 35% efficiency. So it's definitely not consistent with our understanding of entropy. Now, if the person came in and made these claims, almost certainly some of the numbers were mismeasured, or they're just making this stuff up. That's another possibility. Unfortunately, if you go online, you do find a lot of these claims that people have come up with these engines that operate at amazing efficiencies. And it's been a year or two ago, but I have to say, I was watching news. I was watching news on TV, and I was actually watching on PBS, on public broadcasting. So I was surprised when they introduced a story saying that engineers in somewhere had come up with a new device that could actually operate on water. So, and what the claim was, they met with these so-called scientists, and the scientists made a claim. They said that they had come up with a new device that could take water molecules and could separate the hydrogen from the oxygen using no energy at all. And then they could return the hydrogen and oxygen together, react them chemically in a hydrogen fuel cell, in a fuel cell. So they were using water, pouring it into what they claimed was a fuel cell, and they had a light bulb on top, and the light bulb would go on. And I couldn't believe on the news hour, PBS NewsHour, that they actually had these totally fraudulent people demonstrating this. And it was kind of funny because they had a little box there, and they had some light bulbs on top, and they would pour the water in, and when they poured the water in, the lights would go on. Somehow that was proof of what they were developing. Now, you know, it's almost certain. I mean, we have so much confidence in these heat engines and designs of heat engines that we've come up with. We don't know of any examples that contradict the principles that we've kind of set out here. But, you know, it's always worth looking at something. If there's a way to look at something and kind of analyze it and see if you can figure out quickly if it makes any sense, or can they actually demonstrate, right? So can you actually demonstrate that this really is working? Maybe there's something new that we don't understand, but there's a good chance that some of the numbers that this person is claiming are off somewhere. All right, so there's a different cycle that we want to look at here. We looked at the Carnot engine. We're going to come back here and look at what is called the Otto cycle. This is kind of funny because this is what we use in internal combustion engines in our automobiles. Okay, so it seems appropriate. It's the Otto cycle. Now the Otto cycle, unlike the Carnot cycle, this consists of a couple of adiabats, two adiabats, same as before, but instead of the isotherms, it has constant volume. So this is a better representation of what we saw when we had that several slides back, right? Right here. So the Otto cycle is, so remember that slide. Okay, and so what's happening here is if we start at A and we compress the fuel-air mixture to point B, and we're going to do that adiabatically. So adiabatic, how can we make something adiabatic? Any engine that's operating very quickly, it's likely that at least some of those processes are approximating adiabats. Heat transfer takes time, and so when we rapidly compress, often that process can be simulated as an adiabat. And then we ignite the fuel-air mixture. And when we ignite the fuel-air mixture, initially at least, the volume is fixed. The piston has come up, there's a certain fixed volume there, we ignite the mixture, and the pressure just rises very rapidly. And so this pressure rises rapidly to here, and then here is the force. We've generated a lot of pressure, and then the pressure from that pushes the piston backwards, back out, and that's where we get the work produced. And so this is a better representation. And then once the piston's all the way out at maximum volume, we open up an exhaust valve and let this stuff out. So it's cycling over and over again. So actually, usually this is kind of a two-stroke engine instead of four, but we're not going to worry about that. CD is the power stroke. DA, we're going to say, is the exhaust. That seems fine. So let's take a look at this. So let's show that for an Otto cycle, the efficiency formula is given by 1 minus volumes. Now, ratio of volumes to the 1 minus gamma. Now, gamma, if you remember, we went through that pretty quickly in chapter 19, but gamma is defined as the ratios of Cp to Cv for the gas that's inside this chamber. And then VA over VB is considered the compression ratio. So so VA over VB, VA was the full volume when the piston's fully out, and then VB is that much reduced volume. And what it says is that we can actually write the efficiency of an Otto cycle in terms of the compression ratio to this power. So we're going to assume the gas inside is diatomic, and let's take a look and see how this would work. Okay, so I got my PV diagram set up again. I've got a couple of, now these are adiabats. They're not constant temperature. They're actually adiabats. And then I've got a couple of constant volume processes. So VA equals VD and VB equals VC. Now QAB, if I'm in one of these adiabats, QAB or QCD, those are going to be equal to 0. Okay? So those we can just kind of ignore in terms of heat. So this engine also has the kind of the feature that all of the heat is coming in just along one of the branches, and the heat is also leaving along one of the branches of the cycle. Now, it's not a constant temperature, so it's not going to have the simple formula that the Carnot engine had. But what we can do is identify what is QH equal to. Well, this is heat going into the gas during a constant volume process. So we'll write this as the number of moles times the specific heat, molar specific heat at constant volume. And then I can write that as Tc minus Tb. That's going to be my QH. Now, the heat leaving from D to A, the QL, that's also going to be NCV. Td minus Ta equals QL. Let me make sure I got that right. Okay, good. So these four temperatures are all different. Those aren't going to cancel out. But the number of moles is the same, and the molar specific heats are the same. And these are both being written down, so they'll be positive quantities. So what I can do is this. I can say, okay, fine, the efficiency for this cycle is going to be 1 minus QL over QH. That's what we're going to have for the efficiency for this particular cycle. And what I can do now is I can take the QL, divide by the QH. When I do that, the N's and the CV's cancel, and I'm left with this ratio of temperatures. So now I have the efficiency in terms of all these different operating temperatures at the different locations within the cycle. Now I can use the adiabat formulas again. So here's my adiabat formula. I'm going to take these temperature ratios and rewrite it in terms of volumes. Now why am I doing that? Because that's what they wanted me to do. So they wanted to get an answer not in terms of temperatures, but in terms of compression ratio. They wanted in terms of volumes. So that's what I'm doing. I'm trying to get these temperatures converted over into volumes. So that's what I did. I took the TD, and the other side of that adiabat is temperature C. So I was able to write TD as TC times this ratio of volumes to be R over CV. Now I did the same thing with temperature A. Temperature A could be rewritten in terms of temperature B. So what I did was I got temperature D rewritten in terms of temperature C, and TA rewritten in terms of temperature B, and so the temperatures cancel out. So what this is saying now is that TD minus TA is equal to TC minus TB times the ratio of the volumes. So I'm operating between two volumes, right? Volume A and volume B. Volume C and D just match up with A and B. So here is my compression ratio, and it is to the R over CV value. And so that is the formula. And they gave us a number. Let me check this back. Yeah, so here they had given us, they said derive the formula and then assume a compression ratio of 8. What would the efficiency of this engine be? So notice that this is the inverse of the compression ratio. So what that's telling me is I get the compression ratio higher and higher, I get the efficiency to be higher and higher. Okay, and all right, so putting in all the numbers, it's diatomic, so I put in 5/2 R for CV, and R over CV is 2/5. So that's it, that's the formula, and that's the efficiency. Now if I go back to here, notice they wrote this in terms of gamma, but gamma is CP over CV, so if I plug that back in, I am going to get CV minus CP over CV. What that's going to become is R, so it's just a different way of expressing this. And then I wrote this in terms of the inverse of the compression ratio, which I think makes more sense, rather than using a negative exponentiation. I have a positive exponentiation there. Anyway, that seemed to work. And so that's another example. We now have the Carnot engine that we looked at, and now we have the Otto cycle, or the Otto engine, that we've looked at. And then in some of the practice problems in the textbook, and in some of the practice problems for the midterm, which is coming up, midterm's coming up, I have some more sample problems that are probably, I'm going to say they're easier, I guess. I've got some sample problems that use constant volume and constant pressure. Take a look at those also. So there are practice problems for the midterm, and there's a key available. All this is in Canvas. So take a look at the practice set of problems, take a look at the key, work through those examples too. Those are a little easier than these. These are a little more arduous, but they're kind of fun to see if you can work your way through the puzzle. All right, I think I'm going to stop there for today. I think what we'll do is we'll come back next meeting and we will introduce refrigerators. And well, let me just do an intro here, and then we'll kind of repeat it in the next one. I think we do have a few more minutes here. Let me just check the time really quick. Yeah, we do. We've got a few more minutes here. So we had mentioned earlier that to take a heat engine and turn it into a heat pump or a refrigerator, that you could just reverse all the arrows. And so what we do with a refrigerator is we take heat out of a already cold region, right? Refrigerators are kind of amazing. Imagine life without a refrigerator. And we take heat out from an already cold region, and we move that, we transport that heat and release it to a high temperature region. So that seems kind of like a remarkable thing to do. So now the way we do that, it wouldn't happen spontaneously. What we have is we have work coming in, and we specifically in a refrigerator, something like this, a refrigerator, we have a compressor. So we have a compressor inside that is able to bring the gas to a really high pressure, or the coolant to a really high pressure, and then the gas is released through a small opening into a low pressure region. And when we release that coolant or that material into the low pressure region, it drops in temperature dramatically. Okay, so this is an example of playing around with these PV diagrams and trying to analyze how can we come up with a PV diagram that will, and here we go, here's the refrigerator. So I'm going to plug this in. Here is a compressor. And what the compressor is doing is it's pushing, there's a pump in here too, it's pushing coolant through a bunch of pipes. Okay, so far not a big deal. But what they've done is, halfway along here, what they've done is they've put what's called an expansion valve. What they've done is they've put a small opening that controls the coolant. And what that expansion valve does is it maintains a high pressure, high temperature. Now here they're saying it's vapor. High temperature, high pressure material on this side, the coolant as it's pushed through. And then on the other side of that valve, it cools down, and often inside, see if they mention, and they say vapor still. So you can have phase changes that are taking place in these coolants also. So anyway, so there's a high pressure, high temperature region that is maintained from a compressor. And then this valve creates on this opposite side a cold region. So the coolant inside, released through this valve, drops in temperature dramatically, and then as that makes its way through, that draws thermal energy from inside the refrigerator. These coils on the outside of the refrigerator are hot, right? If you've touched a refrigerator, or if you've seen a refrigerator that just has coils on it, you know that these are at high temperature, and then the pipes running through the center are at low temperature. So by running this compressor, we generate a high temperature region, a low temperature region. We put the low temperature region inside the refrigerator, we put the high temperature region outside, and we draw QL from inside the refrigerator, and we release QH to the outside. And it is it's remarkable. It's an amazing process. Okay, certainly I'm going to go ahead and stop there. So we'll pick up with this. We'll pick up with refrigerators next time.